So hi, Epox, welcome to the video. Let's directly jump into the Leetcode daily challenge. Let me open Leetcode. Yeah. So today is 3rd of October and day 3 of October challenge, and we will be solving typing in water 2 problem. I recently got to know that this problem will be easily opened from there, so we can try there. Yeah. So have you noticed something is scheduled maintenance at 10 p.m. UTC? 10 p.m. UTC means 10 plus 5:30, like 12 and 3:30. It's like 3 2. So after half an hour, it will be like down for 10 minutes. We will be done by that, I think. So today's problem is trapping rainwater 2. Let's directly jump into this. Okay, so what the problem is saying, given mcros and integer matrix height map representing the height of each unit cell in 2D evolution map, return the volume of water it can trap after raining. Okay, something looking like it's a 3D version of famous trapping rainwater problem. Have you solved trapping rainwater problem? Please let me know in comments. If not, we will discuss trapping rainwater problem first. So after that we can come to this video. So explanation of that or base building from that problem is very important. So we will again go to our problems, and we will first open trapping rainwater one. Trapping rainwater problem, which I have solved. I think in 2021 I have solved this. Let's try again. So I will explain the problem first, and what's the intuition behind it, how we can approach this problem, and after that we can jump into the today's Leetcode daily challenge. So I think my screen is visible. Also, yesterday's video there is one problem that whenever I started to drawing, the recording stops. So which I have solved, and it should not be happening in today's video. So I will make sure before uploading that this should not be the case for today's video. Let's start. Okay, so we have a given n non-negative integer representing an elevation map where the width of each bar is 1. Compute how much water it can trap after raining. Okay, so we have some, this is like 2D version of that trapping rainwater, and you can assume that we have something hilly areas, something like that, hills. Okay, and the water will be trapped between these. If you see, 1 minute. Mm. Yeah, so it will be like something here, and some water will be trapped here, and if this is the case, there is no water trapped here, and some water will be trapped here, and no water will be trapped here. Okay, so we have to find the area, how much water here, 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 and here is trapped. Okay, so let's understand this better via this example. So example number 1, we have given the height. So height is 0, then height is 1. It's fairly illustrated in the image, so you can understand from there as well, like 0 1. Okay, after that we have 0, so we can trap 1 unit of water here, because after that we have a big wall of 2 unit here. So total water trapped here, it will be like 1 here, 1 1 2 here, and 1 here. So it will be like 6 unit of water will be trapped here. Okay, so the concept here is, from the physics you can understand that water will not overflow here. If we can like trap 1 unit of water here, so it will be overflowed by this wall. So water will be trapped only if there is a left wall and right wall, and both of them is bigger than, there is some area basically. So we have some deep uh, deep area where we can trap the water. There is a something is left wall, something is right wall. So whatever is the smaller wall, we can trap that much of water in that area. If right wall is smaller, then we can trap like minimum of right comma left comma right wall. We can trap that much water in our particular area. So we somehow has to keep track of what's the left height of left wall and height of right wall. So here if you see that we have a left wall size is 2, then 1, and if we come to this position, we will say left wall height is 1, which is not true. Like we have to keep track of maximum height of left wall which we have seen. So here we have seen 2, and from this side we have to track maximum height of right wall we have seen, which is 3. So which is smaller? Obviously 2. Then we can trap 2 unit of water here. Basically 2 is the size and minus the size of already filled land here. If there is a land here 1, say we can trap only 1 unit of water here. Understood? So that's the concept. So you understand that we have to keep track of what's the maximum height we have seen from the left and what's the maximum height we have seen from the right. So we can approach this problem something like key. We do some pre-processing, and in pre-processing we compute what's the left wall we have seen maximum value, and we track of right wall and what's the max value we have seen. So let's try run on the example number 1 and 2 and to see this in action. So in our first example we have a height of 0, 1, 0, 2, 1, 0, 1, 3, then 2, then 2, oh my bad, 3, 2, 1 to 1. Okay, so what's the left maximum we have seen from here? We will take L max, left max. So here we have seen 0, here we 1, then maximum of 1 comma 0 1, maximum 1 comma 2 2 we have seen maximum, then 2 2 2, this will become 3, and after that it will become 3. So this is the left wall height we have tracked. Similarly we will track right wall height, what is the maximum we have seen, and to track this we have to traverse the array from behind to front. So we will traverse something like 1, then we have seen 2, maximum 2, 2 comma 2 comma maximum 2, here it's become 3, maximum we have seen 3, then it will be 3 3 3 3 3 3 and 3. So after this pre-processing step we have one array which is called left max, we have one array which is called right max. Okay, and for each iteration we can see that for this index I, for each index I we can see how much maximum left wall height, what's the max of right wall height. We will take the minimum of both and we will subtract the height of I. So the water trapped at high, water trapped of I position will be minimum height of left maximum wall, right maximum wall minus height of I. You can understand something like this. So this way we can traverse the complete array, and I will traverse for dry run purpose here. So 0 comma 3 minimum is 0, 0 minus 0 is 0, then 1 comma 3 minimum is 1, 1 minus 1 is 0, then 1 comma 3 minimum is 1, 1 minus 0 is 1, then minimum is 2, 2 minus 2 is 0, then minimum is 2, 2 minus 1 is 1, then minimum is 2, 2 minus 0 is 2, then minimum is 2 and 2 minus 1 is 1, then minimum is 3, 3 minus 3 is 0, then minimum is 2, so 2 minus 2 is 0, then minimum is 2, 2 minus 1 is 1, and then minimum is 2, 2 minus 2 is 0, and minimum is 1, 1 minus 1 0. So we have total 1 plus 1 2 4 5 6 unit of water trapped here let's look at another example number 2, which we have height as 4 2 0 3 2 5. Okay, what's the left max height we have seen till now? We have seen 4 4 4 4 4 and 5. What's the right maximum height we have seen till now? We will track from the behind. 5 5 5. It will be 5 always. Okay, now we will iterate over this array after this pre-processing step, and we will do calculation how much water is trapped. So 4 comma 5, minimum of 4 comma 5 is 4. 4 minus 4 is 0. Then minimum is 4. 4 minus 2 is 2 unit of water trapped. Then minimum is 4. 4 minus 0 is 4 unit of water trapped. 4 minus 3 1. Then 4 minus 2 is 2. Then 5 minus 5 is 0. So 2 plus 4 plus just a minute. 2 plus 4 plus 1 plus 2 6 7 9. So total 9 unit of water is trapped here, which is the answer. Okay, so this took the how much time complexity we have taken. We will compute this left max array. It will take n time considering the n elements of the array. Then we will process the right array, which will another take n time, and then we will iterate once to find the total sum. So it will be another n time. So total we have seen 3n, which is order of n time. And how much space we are using? We are using n space for left max array. We are using n space for right max array, and total we are using for this iteration we are not using any space. We will keep the running sum, like something like answer plus equal we will do, and we will keep adding these integers, whatever the trapped water at that location, control is to our answer. So this is order of 1 only, but for these two arrays we will taking 2n space, which is order of n space. So we have solved from order of n. We can further optimize this, and I don't think so we need to do left max array computation. We can keep the running left max. So since we are going from I to j, we can keep running left max, and we can avoid this array altogether, which will be doing our like space complexity will be from 2n to reduce to n. Only one array we will keep, the right max array, and it will be like order of n, but still our space requirement is half. This is the general intuition it will come. So more optimal approach is interviewer can ask that can you solve it in order of n time and order of 1 space. So there is a 2-pointer approach here, which can be solved this problem in order of n time complexity and order of 1 space complexity. To solve this problem, and the intuition is that from left and from right we will keep 2 pointers at 0th position and at n minus 1 position, like last index and first index. We will keep, just a minute, we will keep 2 pointers, and we will check that what's the maximum at the left we have seen till far, and what's the maximum we have seen in the right. So this pointer will be go from 0 to n in positive direction, and this pointer will be go from n to n minus 1 to 0 in negative direction. They will meet somewhere in middle. So the idea here is to keep track of right maximum also running, left maximum also running, and keep computing number of water trapped based on that, how much water is trapped. So remember example we have I have shown in the initial phase of this problem. So let's say we have some problem like something like this, some hills, okay, and let's do this. So no water will be trapped here since there is nothing left max, which is like, let's take this position I. If this is the I, there should be a left max we have seen, which is greater than this to trap this water, which is not. So we will keep going up till here. After that, in each point of here we can see there is left max which can trap water, and there is something makes it right, which will also track, like trap this water. So we will be doing calculation based on this left max we have seen till here. So this will be our field water. After that, this hilly area we can completely ignore, something like first hill. And after this complete calculation will go on like this. Similar to this approach, like from right, we are also going from right to uphill, and we will trap some water here and some water here. It will be more understood when I code this problem, but you understand the intuition behind it. There is one more approach to solve this problem using stack. I will show you once. Let me clear this drawing. So like in topics you can see stack is also monotonic stack, and stack say you can solve this problem. So how to approach that? That's the tricky one. So remember I have drawn some mountains here. In the mountains we find some peak here. So from this peak we know that from peak we can do something to the left part, and from this peak we can do something to the right part. Okay, we uh, we find solution for that rainwater trapped in the left part, and then we find solution for the rainwater trapped in the right part, and we will sum it up. That's the whole idea, finding the peak uh, and doing calculation for the left part and doing calculation for the right part, because these two parts will never collide with each other. That's the whole idea. And using monotonic stack you can do that. From the left part perspective I can like do a quick dry run for you. So let's take the first example and do a dry run. So we will find the peak. Peak will become here at 3, which is this bigger one. Okay, we will calculate the left part first and then right part. So it will be like 2-pass algorithm. So let's create a stack. So here is our stack. We can start from this, and till 3 we will start, till this point we will start, and from here to here we will calculate going via front direction, and while calculating the second part we will go in reverse direction. That's the whole point of the peak. Okay, so we will add 0 first, then we will get 1. So 1 is bigger than 0, so this will be like monotonic stack. This will be monotonic stack. So we will keep only the smaller element on top of this. So 0 is useless here. Now we will keep 1, and we will keep the max, track of max. So max we have seen till now 0, and 1 is greater than 0. Okay, so we have seen left max is 0. 0 minus 0 is water trapped at that location is 0. We can remove this, we can insert 1. You will understand better after we go 2-3 steps more. So let's understand. Next is 0. 0 will come, 0 will sit here. Left and max will be updated to 1, which we have seen. Then we have 2. So 2 will come, and 2 will say that okay, I can't go up, so remove the elements until everything is bigger than 2 in the monotonic stack. So we will first remove 0. So this 2 will become act as a right pole, and the max we have seen is become as a left pole, which in the original algorithm I haven't explained. So from 1, 2, what's the minimum? 1, and so we can trap 1 unit of water here. So 1 minus 0, which is 1, and then 1 minus 1 is equal to 0. So we have trapped 0, 1 and 0 unit of water, and we remove both of them. We put 2. Then next we have 1, we will put 1, and also we will update this maximum to 2. Okay, let me take another color. Okay, let me create a bigger stack here. So let's create the stack. So currently we have 2 in our stack, then we will come to 1, then we will come to 0, 0, then we will come to again 1. So when this 1 comes, what we will say, that we will remove each and every element which is bigger smaller than 1, and we will put 1 after that. Okay, So till now what is the max we have seen? 2. Okay, so max left we have seen 2, and we have a peak. We know that we have a some peak here, okay, which is not yet reached. So we can trap how much unit of water, whatever the max is there, minus the unit, correct? So max we have seen 2, minus we have seen 0, so 2 minus 0 is 2. So we remove this element, then we will put 1. Then after that next 3 will come, so 3 is the our peak. We will not push it back, and we will remove each and every element by reducing from the max. So 2 minus 1 is 1, then 2 minus 1 is 1, and 2 minus 2 is 0. This way this stack will become empty, and we have how much water we have trapped till now. So we have trapped 1 unit of water here, 2 unit of water here, 1 unit of water here, and 1 unit of water here. So 2, 3, 4, and 5. 5 unit of water we have trapped in left side of that peak. You can actually verify 1, 2, 3, 4, and 5. 5 unit of water we have trapped in the left side of peak. Similar we can calculate for the right, and we can sum up the answer. That's the another approach, but we will code out the 2-pointer approach first, and you will get more intuition and more easy approach that how we are going with 2-pointer. So let's start with coding the 2-pointer approach. So let's first take what's the n value size, and if our array is less than 3, like at least we need 3 bars, so we can trap some water in between. We can't trap on the first bar, we can't trap on the last bar, we have to trap in between. So if n is less than 3, we can simply return 0 without any calculation. This is our base case. After base case, we will do we will keep 2 pointers. So we keep a low pointer which is at 0, and we will take a high pointer which will be at n-1 location. Also we will be keeping running max of left wall and running max of right wall. So we take int left max wall is 0, let's take it -1. So we haven't seen that, or we can take it as 0, no problem. And right max wall also is 0. Okay, so we haven't seen any left max and right max wall, and we will be starting our algorithm from there. So we will keep running while our low is less than high, since they will meet somewhere in the middle type thing, and we don't need to keep track of outer bound index. Because we are going left index, we are increasing left index, we are decreasing right index, and they both meet in the middle until low is less than equal to high. Okay, so there's two condition at location I. So let me explain via this drawing. So at location I, there can be two conditions, right? That we have seen something at left which is max, okay, and we have seen something at right which is max. Okay, so how much water is trapped at location I? How to find that? That's the whole question, correct? Okay, so if this this wall, left wall is smaller and this right wall is bigger, we can find this by if comparison. Then we know that anything here at location I, we can trap until this boundary, okay, not more than that, correct? If right is bigger, if left is bigger, reverse is true. Okay, so we will code this condition first, and I will explain after that if there is any doubt. So if we have seen left max wall which is less than equal to right max wall, then we will do something else. We will do Okay, there's the moon agenda. So we will do reverse here. In the left max, when the left max is less than equal to right max, means left wall is smaller than right wall. There is one condition. If height of low, we will check height of low. What is the height of low? If this is smaller than your left max, what we have seen, then to I will calculate something, right? If this height is greater than equal to my left max, then I can't wrap any water, and I will directly just update my left max to what I have seen, height of low. Correct? If that's not the case, if, then what we will do, we will calculate how much water we have trapped here. So let's keep a variable water trapped equal to 0, and how much water is trapped here. Water trapped equal to water trapped plus something, some water. Okay, how much water? Whatever we have seen from the left wall minus what's the height of current cell. That means that much water will be trapped here. In the else condition, we will do exactly opposite of this. So if height of our high element is bigger than our right max, then I will update right max first. Height of high pointer, and in case of that's not the case, we will add our water trapped. Water trapped equal to water trapped plus how much water is trapped, because this is the case that left wall is very big, right wall is small, so we can trap up to right max. Okay, so up to right max minus whatever the height of current high. That's the case. And after this operation, we have to do high minus minus, because we will move one step back from the right, and in this case we will do low plus plus, which we will move in front. Okay, and we will return water trapped at the end. Let's run this on base test cases. Yeah, there is some error in case number 2. It is saying output is 7, expected is 9. Whenever we found this kind of issue, we will do dry run and find out the problem, which is the actually useful. So we will do dry run on our example number 2, which is 4 2 0 3 2 5. Okay, until now left max is 0, so we will keep two variable here: left max, which is 0, right max, which is 0, low pointer, which is at 0, and high pointer, which is at 0 1 2 3 4 5 5. So we can mark low here, something like that, low, and this is high, this is high. You understand basically. Okay, so whenever is low is less than equal to high, we will go inside this. If left max is less than equal to right max, which is the case because both are 0, we will take height of low. If height of low is greater than equal to left max, so left max we will increase, so left max will be increased to 4. Okay, and we will do low plus plus, so low will come to here. Okay, now in the next iteration, it will still low is less than equal to high. While loop keep running, it will go in else condition, because height of high is greater than equal to right max. Height of high, sorry, it will go in the right max is smaller, so it will go in else condition. In this else condition, we will check height of high, which is 5. 5 is greater than right max, correct? So we will update the right max to 5. So we will update this right max to 5. We'll do high minus minus, so high will come to here. Okay, now in this case, if left max, again it will compare from 4 5. Left max is smaller than right max, so we will go in this above wala if loop, if conditions. So height of low is 2, 2 is greater than equal to 4, wrong. So water trap will be water trap plus water trap is 0, so we will take like water trap equal to 0 plus left max is 4 minus height of low is 2, so 2 unit of water will be trapped here. Okay, plus then we will do low plus plus, so low will become go here. Still left of max is less than equal to left of height, so 4 minus 0 will be 4, 4 unit of water will be trapped here, plus still low will go here, so 1 unit of water will be trapped here, plus now low is less than equal to high, but we haven't calculated for this high, correct? That's the main point. So we have seen 4 plus 2 plus 1 plus 1 1, so 4 6 and 7, so that's why our answer is coming out to be 7, and we are not calculating for this high because low less than equal to high, so we have to add low less than equal to high. That's the condition we forgot, so we'll add that quickly and we'll run this again. Now you understood that two problem approach as well. After this try run you will be better understanding that what's the issue, unknown network error. Let me try it again. I think I got the issue because it's down, website is down now and we are trapped in that. So we are trapped in our site maintenance. Okay, so it will be come back in 10 minutes, so I will meet you in 10 minutes. Yeah, so Leetcode is back. Let's start and let's run this now. Yeah, it's accepted, both the test cases passed. Let me submit. Yeah, it's accepted. 0 ms beat 100%. We are doing 2-pointer approach. What's the time complexity and space complexity of this? So we are doing, we only defining some variables here. Just a minute. Something like a low high and right max light, left max right max and water trap. So all this comes out to be O1 and O1 in space complexity. And for the time complexity perspective, we are doing while loop and we are iterating over the array, one element only one time, so it's off and time in time complexity. Thank you. I hope this will be useful for you, and we will be solving drain trap second part of this problem, trapping rainwater 2 in the next video, since this video will be like too long if I keep going in the same video. So let's meet in the second part of this video so we can solve Leetcode daily challenge and continue with this. Bye.